one, I'm getting into specific types of series. All right, so this is where we add up elements of a sequence. We'll be specifically looking at cases involving infinite series. So what we want to learn is whether or not a series will converge or diverge, and there are specific strategies associated with specific types of series. All right. So once you identify the form of the series, it's pretty easy to connect that to an approach. All right. So we'll start off with these three cases. Well, the first is, first and second are real cases. The third is just other helpful rules, but those other helpful rules are really helpful because they're just kind of reinforcing what you already knew about limits, derivatives, antiderivatives, and that is that constant multiples, sums and differences are going to pretty much play the same role here that they did for pretty much everything else that we've done. All right, so let's look at this example here. The sum going from 1 to infinity of 3 over 2 to the nth power. And you can see the expansion there. It says find the first 10 terms of the sequence of partial sums and list them below. All right. So partial sums is really just talking about, all right, if I wanted to add the first term to itself. Okay, well, that's easy enough. That's 3 over 2. If I want to add the first term to the second term, what would I get? And you're like, whoa, we're really doing this, huh? So we would have to do 3 over 2 plus 3 over 4. You can math enter, unless you want to use the fraction tool, in which case it'll do it for you. So you get 9/4. And you can add the first 3 terms. All right, so I would just add on a 3/8. 21 over 8. All right, and then I would add the next one, which would be 3/16. So I'm going to add a 3/16. And math frac that. 45 over 16. And I'm only math fracking it so that I can have something more convenient to write. But the decimal values actually tell us a pretty good story here. They give us a pretty good idea of what's happening. Right? And the whole goal is to determine, if possible, what the partial sums are approaching. Because then it'll give us a sense, if they are converging on a particular value, of what the actual sum of the series would be. All right. So 2.9065, it seems like we're getting closer and closer to 3, but who really knows? All right, we'll see. Maybe there's a better way to do this. There's got to be a better way to do this, otherwise we wouldn't be here. All right, so we're up to 5 terms of the sequence of partial sums. So next up would be 3 over 64. Alright, so that's adding the next one in. Math frac that one. 189 over 64. Now, you notice patterns when you do this. The bottom pattern hopefully is pretty obvious, right? And that's related to common denominators. The top pattern, maybe less so, but they all do look like they're multiples of 3. So that's helpful, except 3 times 3 is 9, but 9 times 3 is not 21. So it only helps to some extent. But if you can figure out a pattern to help you there, then you can kind of get to the end of the line a lot quicker. But not as quick as the rule that I'm going to show you in a few minutes will get you there. So it ends up being like figuring out the pattern is more for fun at this point, because there are tried and true techniques that'll get us there more efficiently. 381 over 128. So 1, 2, 3, 4, 5, 6, 7. 3 more. I think I'm probably proving the point of just how tedious this can be and how much you don't want to have to do this. I'm going to keep it all in black now. 765 over 256 plus I need to add on 3 over 512. And it does appear to be moving in on 3. So hopefully we're developing a little bit of comfort with the idea that this is going to converge to a 3. But I have been fooled before, so we'll see. Alright, so this should be the last one. Math and our enter. And we got 3069 over 1024. Alright, so what do we notice about the results? What does the formula for the sum of infinite geometric series tell you about this series? Well, what do you know about it? They seem to be approaching 3. Alright. So that's great, but you know, what does the formula for the sum of infinite geometric series tell you about this series? Well, we didn't do anything with that, so maybe it's time. All right, so let's take a look at the series that they gave us and compare it to the series formula or formulas that we're presented with above. Now, first thing maybe you'll notice is that these formulas start off with zeros. Or, I'm sorry, some of the formulas start off with zeros and some of them start off with ones. All right, so you just got to be careful about which one you use. In some cases, like in the case of geometric series, it doesn't seem to be, and for geometric it doesn't seem to be relevant. But in the case of the arithmetic, and for whatever reason we call that arithmetic as opposed to arithmetic, even though it's spelled exactly the same, there is a difference, all right? So you just got to be careful about that, all right? So I have, and I'll just rewrite it here, just so I don't have to scroll back and forth. The sum as n goes from 1 to infinity of 3 over 2 to the nth power. All right. So the rule that we're presented with here says the S for sum all right, is going to be equal to R times A sub 1 over 1 minus R. And it's like, okay, so what is R and what is A sub 1 and all that? Well, if you look at the model, you see here it's slightly different from what we have. But they did say infinite geometric series, so we should be able to match what we have here with what you see above in the general rule. All right, so I'm just going to fix this real quick. So what I'm going to do is first take note of the defining characteristics. It says if the absolute value of R is less than 1, where A is the first term. Ah, the first term, okay. So A sub 1 is the first term. Well, the first term here was 3 over 2. They gave us the expansion, but even if they didn't, we would have come up with that ourselves. And R is the common ratio. All right, so the common ratio is the number that you would multiply each term of the sequence by to get the next term in the sequence. So in each case, we multiplied by 1/2. So R is going to be equal to 1/2. All right, so I would be thinking about, okay, well, if I want to convince myself that this is accurate, I would want to be writing this rule in this form. All right, so the sum from n equals 1 to infinity of 3 over 2 times 1/2 to the nth power. All right, so now I need to convince myself that these two things are equivalent. All right, if I identify the first term of this sequence, based off of this relation, or this expression, I would be replacing the n value with a 1. And so I would have a 3 over 2 times 1/2 to the first power. Now that's going to give me a 3 over 4. Alright, so that's not the first entry here. The first entry is 3 over 2. So we got a problem. It's not a major problem, but it's a little problem. Alright, because if I use this a sub 1 and this 1/2 in this formula, it's going to give me an incorrect sum. Alright, so what I want to do is I want to rewrite this so that it is in the correct form. Now there's two ways to handle this. One would be to manipulate this to get it into the appropriate form, right, algebraically. The other is to sort of kind of logically realize, now wait a second, if this is the second entry, then this must be the first entry in the expansion, or this is the first entry in the expansion. Then if I want the result of this computation to be 3 over 2 instead of 3 over 4, then I probably started with the wrong number here. All right, so I'd be thinking to myself, all right, well, what would be one step prior to the 3/2? All right, so, and by that I mean if the common ratio is 1/2 and we're multiplying by 1/2 every step of the way, why not divide by 1/2? 3/2 divided by 1/2 is 3, so let's try that. So the expansion here would be, again, substitute the 1 for, oh, overshaft the Mac, 1 for the n, so 3 times 1/2 to the first power would be 3/2. That's our first entry, so then we're in good shape. So this one's out, and so that's telling me that the a sub 1 value really should be a 3, right? So incorrect conclusion here. Common ratio would be a 1/2. All right, so now when I apply my rule here, S would be 1/2 times 3 over 1 minus 1/2. Right, 1 minus 1/2 is a half, so 1/2 times 3 over 1/2 gives you a 3, which is what we expected. All right, so that's great. Now, how could we do this without doing all that work? Well, let's take this expression and see if we can work it to be in the appropriate form. All right. So what I can do is I can say, well, I got 3 over 2 to the nth. How about 3 times 1 over 2 to the nth? All right. Now, if I wanted to write this as, instead of 1 over the denominator squared, I could actually assume that the power of the 1 is also n, because 1 to any power is still 1. And so that allows me to rewrite this as 3 to the 1/2, or 3 times, sorry, 1/2 to the nth power, and the summation would come along for the ride. So much simpler. The reason why I kind of take you down this path is because a lot of people do that. They see an expression that looks geometric in nature and they just grab values from it. And they say, oh, okay, well, it must be that the first value here in the expansion is the a sub 1, and the common ratio is the 1/2, so that must be it, when really there's a little bit more to it than that. All right. So you want to have your summation in the appropriate form in order for this to play out the right way. All right. So that should take care of that part of it. Now, if we want to look at this in the calculator, we want to go back into well, actually, not back into it. We're going to go into a different mode. We're going to go in parametric mode. We had been working, I believe, in, oh yeah, sequence mode. So parametric mode. So we're not really learning about parametrics, just we're using the parametric mode on the calculator to help us get an idea of what the expansion would look like. It's kind of cool in that regard. So we're going to also use the dot mode, but we'll get to that in that's a different conversation in a minute. All right. But you can see here, if you go down the mode menu, that there's a lot of different options. You know, you get all these stat options and things like that. So, you know, there's a lot of good things that you can look into. But yeah, we want parametric and we want dot instead of being connected, because we're dealing with, and we talked about this in the last part of the unit, that these aren't continuous functions. They're just points plotted in space. All right, so that we want to have our calculators display that. All right, when you hit y equals, it brings up an x equals and a y equals pairing to give you a single graph. All right, so what we do is in our first equation here, we put a t, and we get that by hitting the xt theta n key. Because again, depending on the mode you're in, it brings up one of these four values. All right. So what that'll do is give us, depending on how we define our domain, any value in the domain of t. You know, so anything from negative infinity to infinity. All right. Now, for the y part of it, we're going to define it in terms of t. All right. So that's where we use the sum sequence. Now you can, there's a shortcut approach here. You know, alpha window. You could use the sum alpha window. You could you could try to use the sum. You know, I almost did it right the first time. I used an absolute value for some reason. I think I just slipped. You could use the sum function here. All right. It does correlate to what I have written there in the YT1. Right? The notation's a little out of whack there. I'll have to fix that at some point. But you just got to keep track of, okay, well, what are the parameters here? So I'll do it both ways just so you have it. But what's going to go in the parentheses is your expression. So 3 over 2 to the t power, which is, you know, we're not using n's here. We could use n's in some instances, but parametrics work in terms of t, so we're kind of stuck with that. All right, so we're going to say 2 to the t. All right, where I have t going from 1 to, well, calculator doesn't understand infinity, so what I say is it's going to go to some variable maximum. All right, so if I keep going with my x equals t, then this summation will keep going. All right. And so when I go into the graph, or not the graph, the table, and let me go to a table set starting at 0 so you really see it. You see all the different entries that we came up with in the first 10 terms of the partial sums. 3 over 2, 9 over 4, 21 over 8, and so on. All right, so all those values are presented for you. Why didn't you just lead with this? Well, honestly, it's one of those things. I don't know how to explain it except to say that I feel like there's not just an appreciation for the techniques that go into all this stuff, but an appreciation for the value of why this stuff is important, or why the shortcut techniques are valuable, when you see just how much of a pain it is to do it out by hand. All right. So it's kind of like if you've ever taken a stat class, the standard deviation. You do it out once or twice by hand, and that's enough to be like, I don't want to do that out by hand every time. So you develop a little bit of appreciation for the technology, and then you move on from there. All right. So that's one way to represent it. The other way is the sum sequence. So second, stat. So you have ops and math. Sum is in math, option 5. Second, stat, ops 5. And then it brings up pretty much the same kind of idea, where it asks you for an expression. 3 divided by 2 to the t, You actually don't need parentheses because of order of operations, but I get paranoid. The variable is t. You're starting at, what do they say, 1, and you're ending at t. And you want to go by ones. So I paste that in, and it has the same notation that I have on paper there. Except it screwed up the, oh, you know what? I must have typed something in incorrectly here, because it's 3 divided by 2 to the t. I must have hit the caret key without realizing it. Apologies. Divided by, because I was like, that looks funny. 2 raised to the t power. Okay, well, anyway, it's in correctly now. But you see it presents it in decimal form this way. All right, there's pros and cons either way. Some people like the decimal form because it gives you a pretty good indication of what it's closing in on, right? And in what way it's closing in on it. So that's also part of the fun. All right, so let's take a look at another example, but this time let's not do it all out by hand in terribly painstaking fashion. All right, so, and I'm going to use the shortcut alpha window summation option 2, t going from 1 to, we can't put infinity, so we're going to go from 1 to t, and we're going to let t continue to increase as far as the calculator will let it. But this time we're going from, I'm sorry, we're using the expression 3 over 2 to the nth. All right, so in parentheses, alpha y equals to get the fraction, assuming you want a fraction. Close it up and raise it to the t power. And then you could take a look at the table, and you see, let's get back to some more reasonable values. The first 10 entries. All right, well, let's get them down. Oh, first 5 terms. Oh, thank the maker. 15 fourths, 57 eighths. Yeah, it gets out of hand pretty quickly. Now that may look like 195 over 16, but we want to make sure. All right, it seems like it makes sense to be that because 2, 4, 8, 16, 32. But sometimes the remaining digits get cut off, so don't fall for that trap. I see a lot of folks falling for the trap of a decimal value that's in scientific notation, and they write like 2.035 when it's really 2.035, and if you scroll to the right, you see it's times 10 to the negative 13th power. So just be careful about things like that. So if you're ever in doubt, scroll down right onto the number and look at the bottom of the screen. So 633 over 32. All right, so what do you notice about the series? Well, we never really answered it for the previous one, but well, we kind of addressed it. What do you notice about the results? What does it tell you about the series? It converges. So we answered it in simple terms, but in terms of the verbiage of the unit, it converges. It converges on the number 3. All right. Now, in terms of these values, maybe it converges, maybe it doesn't. So one thing you can try, now with this, I think they call it math print, doesn't always play out, but usually when you put in a decimal, it'll give you answers in decimal. And it does in this case, which is good. All right, so if I increase, because the fractions sometimes, maybe they're converging, maybe they're not, but this appears to be the case where they're not closing in on one another, or I'm sorry, they're not closing in on a particular value. It seems to get larger and larger. All right, so what do you notice about the results? Getting larger and larger. So we're looking at a case where it diverges.